Hello, everyone, and welcome to my channel, Bio-Ogi with Jorgen. My name is Jorgen, and before we begin our lecture, I want to tell you a little bit about myself. I completed my Mongolian bachelor's degree in 1863, when I was 409 years old. Yes, that's me in the photo. And now our topic is photosynthesis and limiting factors. There are three main culprits we need to talk about. Factor 1, light intensity, the energy spark. Photosynthesis begins in the light-dependent reactions, where chlorophyll absorbs light energy to generate the batteries that power the rest of the process. At low light intensities, the rate is directly proportional to the light available. More light means a faster reaction. But the relationship isn't infinite. As light intensity increases, the rate eventually hits a plateau. The plant reaches its light saturation point. At this stage, the plant's machinery is working as fast as it can, and another factor, perhaps a lack of CO2 or ideal temperature, becomes the new limiting factor. Extremely high light can also damage the chlorophyll. Factor 2, carbon dioxide concentration. The essential ingredient. Carbon dioxide is the vital raw material for the Calvin cycle, where glucose is actually synthesized. Atmospheric CO2 is present in very small concentrations, typically around 0.04%. Because of its scarcity in the air around us, CO2 is frequently the primary limiting factor for plants in nature. As we increase the concentration of CO2, the rate of photosynthesis increases rapidly. The enzymes responsible for fixing the carbon have more substrate to work with. Again, we see a plateau. Once all the available enzymes are saturated, adding more CO2 won't help unless we increase the light or temperature to support that higher processing speed. This is a principle that greenhouse farmers exploit to boost crop yields. Factor 3, temperature, the enzyme sweet spot. Photosynthesis is a series of complex biochemical reactions, all catalyzed by enzymes. Enzymes are protein sensitive to temperature changes. At low temperatures, molecules move slowly, leading to a slow rate. As the temperature increases, the rate of photosynthesis increases, often doubling for every 10 degrees Celsius rise until it reaches an optimum point. But go too far, and you have a problem. High temperatures cause the enzymes to denature. They lose their shape and can no longer function. The rate of photosynthesis drops off rapidly. The optimal temperature varies between species beyond the big three: water and chlorophyll. We should also briefly mention water. It rarely acts as a direct limiting factor for the chemical reaction itself. However, water indirectly impacts photosynthesis immensely. When a plant experiences water stress, it closes its stomata, tiny pores on its leaves, to prevent water loss. Closing those pores also shuts out carbon dioxide, making CO2 the immediate limiting factor. And finally, the concentration of chlorophyll itself matters. Nutrient deficiencies can limit its production, limiting the plant's ability to absorb light energy. And a little bit history, Black man's law. The weakest link. In 1905, F. Blackman articulated the law of limiting factors. It states that when a process depends on several factors, its rate is determined by the factor that is nearest to its minimal or least favorable value. Think of it like an assembly line. You might have unlimited materials, but if one robot is slow, the entire line is capped at that slow pace. In photosynthesis, the slow robot can be one of several conditions. The three primary limiting factors are light intensity, carbon dioxide concentration, and temperature. And that concludes our little lecture.
I don't know why, it doesn't even matter how hard you try. Keep that in mind, I'm designed and trying to explain in due time. All I know, time is a valuable thing. Watch it drop by, it's a pendulum swing. Watch it count down to the end